Hello, Matthews Gatos here. In this video, we're going to be looking at Chapter 5, Sections 1 and 2, which are vertical and horizontal asymptotes. So let's begin with the vertical asymptote. A vertical asymptote is a vertical imaginary line that the graph approaches but never actually touches or crosses. The reason that it doesn't cross it is because it is based on a non-permissible value. And that non-permissible value is found by looking at factors or values of x that would make the denominator 0, because we can't divide by 0. Now, not every non-permissible value is a vertical asymptote. If we have a removable factor, that is not a vertical asymptote. It is actually a point of discontinuity. So vertical asymptotes correspond to an infinite discontinuity, and I just want to look at a couple of visual examples of what vertical asymptote and the behavior about them look like. So for example, here I have two-sided limits, and I'm approaching this asymptote at x equal to a. So let's look from the left. As I approach x equal to a, I'm going to positive infinity. From the right, I'm also going to positive infinity. In this one here, I'm going to approach a from the left, but this time you see I'm going to negative infinity. Approaching it from the right, also going to negative infinity. Let's look at some one-sided limits. So from the left, I'm approaching and I'm reaching positive infinity. This one from the right, getting closer to x equal to a, I'm going to positive infinity. Now, one-sided limits can also go to negative infinity, such as this one here, going from the left closer to x equal to a. You see I'm going to negative infinity. And from the right, approaching x equal to a, I'm also going to negative infinity. So the formal calculus definition, a vertical asymptote x equal to a exists if the limit as x approaches a of the function f of x is equal to positive or negative infinity. So in these examples here, we're really building towards curve sketching without a calculator. So in these examples, we are going to determine the vertical asymptote through factoring, find critical values, and use those with a number line for sign analysis to figure out the behavior on either side of the asymptote. So let's look at our first example. So I will factor the numerator and denominator. So numerator can't be factored. Denominator can be factored like this. So let's look at our critical values and talk about what those mean with the graph. So I have a critical value at 0, but because it's in the numerator, that corresponds to an x-intercept. I have a critical value at 3, and because it's in the denominator, that corresponds to a vertical asymptote. I also have a critical value of -2. Because it's in the denominator, it also corresponds to a vertical asymptote. So we're going to use these critical values with the number line to see the behavior on either side of the asymptotes. So let's start with our numerator. So our numerator, x, is 0 here at 0. So to the left, the factor will be negative. To the right, the factor will be positive. Okay, let's go to x plus 2. So that is 0 at -2. So to the left it will be negative, to the right it will be positive. And then our last factor, x minus 3, is 0 when x is 3. So to the left it will be negative, to the right it will be positive. So putting this all together, to the left of -2 I have 3 negatives, which make that negative. So that means to the left of the asymptote at -2, I will be going to negative infinity. To the right of -2, I have 2 negatives, which make that positive. So to the right of -2 asymptote, I'll be going to positive infinity. To the left of 3, I have 1 negative. So that means to the left of x equal 3, I will be going to negative infinity. To the right of 3, I have all positives. So that means to the right of 3, my asymptote will approach positive infinity. So this just gives us an idea, beginning of the behavior on either side. Let's check that in the calculator. So you can see negative infinity, positive, negative, and positive. So I know I did that correctly. Okay, let's try another example. So in this one here, factoring the numerator, difference of squares, and factoring the denominator. Okay, I see I have x plus 1 in the numerator and denominator. So I'm left with x minus 1 over x plus 6. So a critical value of positive 1 in the numerator and negative 6 in the denominator. So let's talk about these parts. So the positive 1 in the numerator tells me I have an x-intercept at positive 1. The negative 6 in the denominator tells me I have a vertical asymptote at negative 6. Now let's go back to this factor that I removed here. I can't just ignore that. So I do have a restriction that x cannot be negative 1, but it will not produce a vertical asymptote. Because it is a removable factor, it will be a point of discontinuity. So at negative 1, there will be a hole in the graph. The point of discontinuity, negative 1 and negative 0.4. So using my critical values here, I'm going to use a number line and do sign analysis. So let's start with our numerator. Our numerator of x plus 1 is 0 at 1. So to the left the factor is negative, to the right the factor is positive. The denominator x plus 6 is 0 at negative 6. So to the left that factor is negative, to the right that factor is positive. So let's look at to the left of negative 6. To the left of negative 6, it is positive. So that means to the left of my vertical asymptote, I will be going to positive infinity. Here I have one negative to the right of 6. So that means to the right of the asymptote, I will be going to negative infinity. So again, I just like to check that behavior on either side of the vertical asymptote on my calculator. And you can see here, positive infinity, negative infinity, so I know I did that correctly. Okay, horizontal asymptotes. So horizontal asymptotes are an imaginary horizontal line that the graph approaches as x approaches positive and negative infinity. Because of that definition, I know that it is talking about the end behavior. So since we're focused on the end behavior, what the extreme ends of the graph are doing, I can still cross a horizontal asymptote in the middle because it's not based on a restriction. It's not based on division by 0. So the graph can cross the horizontal asymptote. It usually happens in the center of the graph. Let's look at some examples. So in this example here, I want to look at the limit as x approaches positive infinity. So as I make x infinitely big in the positive direction, you can see it's approaching that horizontal asymptote y equal to L. Again, as x approaches positive infinity, as I get it really big in the positive direction, you can see it approaches that horizontal asymptote at y equal to L. Okay, over here. So as I make x infinitely big in the positive direction, you can see that that distance between that line is getting smaller and smaller, so it is approaching that horizontal asymptote towards negative infinity. So as I make x big in the negative direction, it gets closer and closer to that horizontal line, y equal to L. Over here, as x approaches negative infinity, so as I get x big in the negative direction, it also gets closer to that horizontal asymptote. This one here is a unique example because it has two horizontal asymptotes. So let's look as I make x infinitely big in the positive direction. You can see I approach y equal to m. If I approach in the negative direction, so if I make it big in the negative direction, I approach a horizontal asymptote of y equal to L. So a horizontal asymptote y equal to b exists if the limit as x approaches positive and negative infinity of the function equals to b. Let's try an example. So for this one here, I want to determine the horizontal asymptote for the function and then sketch the behavior of the curve near that asymptote. So what I'm going to do is take the limit as x approaches infinity. So I want to look, as I make x really big, what's going to happen to this function here. So I'm doing this, and I'm going to use that rule, the limit as x approaches infinity of 1 over x to any power, because I know that equals 0. If I have a really big denominator, 1 over a really big denominator is going to get closer to 0. So I'm going to use that rule, and in doing so, I'm going to multiply top and bottom by 1 over x to the highest power. If I do it to the numerator and denominator, it's fair. I haven't changed it. So the limit as x approaches infinity, x times 1 over x squared over x squared times 1 over x squared plus 1 times 1 over x squared. So I know this one goes to 0 and this one goes to 0. So I have 0 over 1 plus 0, which is just 0. So that tells me that my horizontal asymptote is at y equal to 0. So I want to look at the ends of the graph, the extreme ends of the graph. Am I above or below? So let's start with the negative direction. I want to test a really small number. I'm just going to always go with positive and negative 100. So if x was negative 100 and I put it into this original function, would I be above 0 or below? So plugging it in, you can see that I am, compared to the horizontal asymptote at 0, I am actually below. So I know the ends of my graph will be below. Okay, let's look in the positive direction. As I make x really big positive, let's take the number 100. If I plug it into the original function, you can see that I get a positive number. So the horizontal asymptote is y equal to 0, and in this case, I will be above. Just like that. Okay, so again, let's check by putting this graph into our calculator just to see if our behavior is correct. You can see here I'm below and here I'm above, so I know I'm correct. Okay, in this example here, I want to show it has no horizontal asymptote. So I'm going to look at the limit as x approaches infinity of x cubed plus 1 over x. So again, I'm going to use that strategy of multiplying numerator and denominator by 1 over x to the highest power. So I'll have the limit as x approaches infinity of x cubed times 1 over x cubed is 1. 1 times 1 over x cubed over x times 1 over x cubed is 1 over x squared. So this will go to 0 and this will go to 0. So I have 1 plus 0 over 0. And that is a problem. I cannot divide by 0. So this limit does not exist. Let's check that on the calculator and see if this graph in fact has no horizontal asymptote. So this is what the graph looks like, and you can see the ends of the graph don't approach a specific value. They actually go to positive infinity, so I know that that is correct. Okay, let's look at a different way of doing horizontal asymptotes. So another way that we can do that is using long division. So I can use long division and write the function as this division statement here. So polynomial divided by polynomial is the quotient plus the remainder out of the divisor. When I do that, y equal to q of x is the horizontal asymptote. So since I'm looking at this horizontal asymptote and I'm adding on a remainder, if I am adding on a positive number, I am going above the horizontal asymptote. If I add on a negative number, I'm making a smaller number and I'm going below the horizontal asymptote. So I can look at the limit as x approaches positive and negative infinity of that remainder to see what exactly is happening. Okay, so let's do long division to figure out what the horizontal asymptote is. So I'm going to have x plus 4 divides into negative x plus 1. So negative x divided by x is negative 1. Negative 1 times x plus 4 is x minus 4. And then I subtract. So I get negative x take away negative x is 0. 1 take away negative 4 is 5. So I know that this fraction can be written as negative 1 plus my remainder out of my divisor. So this here is my horizontal asymptote. So I have a horizontal asymptote at y equal to negative 1. I'm going to look at the remainder to figure out what exactly is happening on either side of the horizontal asymptote at the extreme ends. So let's do the negative first. I'm going to look at the limit as x approaches negative infinity of 5 over x plus 4. So a really big negative number. So if I have 5, which is positive, divided by a really big negative number plus 4, it's still going to be a negative number. And a positive divided by a negative is a negative. So I should expect to see, as x gets really big negative, the graph should be below the horizontal asymptote. So I can just check with that test method that I did before. If I take a small number like negative 100, plug it into the graph, my horizontal asymptote was negative 1, and you can see by that number I am below, so I know I'm right. Okay, let's do positive. So I want to look at the limit as x approaches positive infinity of 5 over x plus 4. So 5 is positive. If I have a really big positive number and I add 4 to it, I still have a positive number. And a positive divided by a positive is a positive. So I know as x gets infinitely big positive, I should be above my horizontal asymptote. Again, we can check that using that other method. Pick a big number like 100, plug it into the original equation, and you can see compared to my horizontal asymptote at negative 1, you can see that number is bigger. So it is, in fact, above. Okay, last example I want to do with you, I want to put vertical and horizontal asymptotes together. This last question here, just checking it here, I was below and above, so I know I did it correctly. Okay, so this one here again, vertical and horizontal asymptotes together. So if I look at my original function just before I get into this, I'm going to look at my numerator set to 0 will give me my x-intercept. So 4x plus 5 set to 0 will give me an x-intercept of negative 5 over 4. So negative 5 over 4, I have an x-intercept right about there. Let's look at my y-intercept. I know that my y-intercept, I don't have an x value. I set x equal to 0. And then I look at what's left, and it's the ratio of the constants. So I know that I have a y-intercept at 5 over 3, and I can plot that. Okay, so I have my x and my y-intercepts. Now I want to figure out my horizontal asymptote and my vertical asymptote. So let's start with vertical asymptote first. So if I look at my function here, first thing I'm going to do is factor the negative so that my leading coefficient in my denominator is positive. I always want a positive leading coefficient. Okay? So looking at this, I can figure out what my vertical asymptote is. So I have set this equal to 0, and I know that I'm going to have a vertical asymptote at 3 over 2. So at 3 over 2, or about 1, or at 1.5, I'll have a vertical asymptote. So I want to look at the behavior on either side of my vertical asymptote, and I'll do that using sign analysis. Okay, so first thing I know is that I have this negative here, so it's negative in every single spot because it's a constant. Then I'll look at my numerator, and that is 0 right here. So to the left it will be negative, to the right it will be positive. Then I'll look at my denominator, and that will be 0 right here. To the left it will be negative, to the right it will be positive. So I'm interested in the behavior on either side of my vertical asymptote. So to the left of my vertical asymptote, 2 negatives make it positive. I know this is positive. to the right of my vertical asymptote, that's negative. So I know to the right of my vertical asymptote, I will be going to negative infinity. Okay, so now let's look at horizontal asymptote. So to figure out my horizontal asymptote, I'm going to use long division. So let me just give myself a little bit more room here. There we are. Okay, so I use long division. So I'm going to look at negative 2x plus 3 divided into 4x plus 5. Okay. Okay, so 4x divided by negative 2x is negative 2. Negative 2 times negative 2x plus 3 is negative 4x minus 6. Subtract. I have 4x take away. Oh, let me try that again. Sorry. Yeah, that's right. Okay, so 4x take away the 4x. Here we are. Negative 2 times negative 4x is negative 4x. Negative 2 times 3 is negative 6. Okay, I got it. So 4x take away 4x is 0. And then 5 take away negative 6 is 11. So I know that my rational function can be written as negative 2 plus 11 over negative 2x plus 3. So this is my horizontal asymptote at negative 2. So horizontal asymptote at negative 2. Now I'm just going to look at the behavior on either side. Okay, so I'm going to test a really small negative number, for example, negative 100, and just see compared to the horizontal asymptote of y equal to negative 2 where it is. Okay, so I plug that in and I can see that compared to negative 2, it is actually above. It's a bigger number, so I know it's above my horizontal asymptote. So it'll be like this. Okay, let's test a really big number, for example, 100, and we're going to compare that to negative 2. And you can see here, it's just below. Okay, so what I want to do is I want to put this all together and kind of connect the important parts together to figure out what the graph actually looks like. So piecing everything together here, I can see that these two pieces here have to be connected. So I know it's probably going to curve around like that. Again, it's just a sketch. Okay, connecting these ends of the graph and passing through the x and the y intercepts, it'll be something like that. And again, we're just looking for a rough sketch right now. Okay, so let's put that into our calculator and see if that looks right. You can see on the calculator, pretty darn good. Okay, so that's pretty much what I wanted to cover in terms of vertical and horizontal asymptotes. I have a little hint for you. Vertical asymptotes are often referred to as MC hammers. So remember, vertical asymptotes can't touch this because it's based on a restriction. So you guys see your homework questions that you want to do, and the next lesson I will do is slant asymptotes.